Hello, this is a remake of the previous video dedicated to homogenization to adapt it to the published version 4. In fact, in the current repository, the version 4.400 is the one which is published, but as there are more than 10,000 packages, the maintainers of the repository ask developers not to update their packages too often because of the load of work involved. So in this page, climatol.eu, you have an access to the latest modifications of the packages. You can just download this file and install it as a local package to avoid installing the version from the CRAN portal. Once you have downloaded it, you can go to your menu or your way of installing packages and be careful to select install from a local package. Okay, so you have also here a guide in English about the best procedures to homogenize climate series with this package Climatol. And here are some videos. This is the one you are watching now. And therefore, let's go to reproduce the example from this guide. This guide, I have it open here. And we go directly to the homogenization procedures because you have already a video on the preparation of the input files. So let's go to homogenization, and for this we will reproduce the examples which are included in the package. Well, first of all, let's start an R session. I will set a working directory, an auxiliary one, which I called auxi0. It's empty right now. And we need to prepare a couple of files for running the examples. These are over here. After we must load the package. You can check that you have the last version, climatol.version, version, and yes, it's 403. And we load the example data, which are included in the package with this command. And now we can go to prepare the files. Prepare files. We had two kind of examples: monthly temperatures and daily precipitations. These are data sets very short because the maintainers of CRAN require that examples must run only in a few seconds, while in real applications of Climatol you will have much more serious and much longer, and they can run from minutes to depending even hours. But let's go to reproduce these examples. With this command we write the stations file. And with this other, we have the data in this object in the data set for examples. We write this into the file which will be containing the data in Climatol format. Okay, we see that we have already now these two files for the temperature, monthly temperatures, and let's prepare the daily precipitations for 3 stations, 1981 to 1995. We can write again the precipitation file the stations. And now we could write also the data file, but this daily data, this series are complete. So for illustrate some of the characteristics of the quality control, we need to delete some data and to introduce some errors. So instead of writing directly this data object, we load it into memory. We will call it DAT. And we have now it in memory. Well, let's go. And now what we do is to delete from the first series the first 300 terms. From the second series we will delete from 1000 to 1200, and from 2000 to 2015. And also from the third series we will delete from term 5000 to 5478. And all of them we assign the missing data code used by R, which is NA, which stands for not available. Okay, and now let's introduce some errors in series 1 from 500 and 509, 10 consecutive terms. We introduce a fixed value of 9.9. In the second series we introduce a negative value at turn 600, and in the third series we introduce in the turn 3000 a very big value like 999. So let's make these modifications, and now we are ready to write this DAT, this DAT object, to the data file for precipitation, for daily precipitation. Okay, now we have these three. For example, in our working directory we have these four files, and we can see that the stations have the format, longitude, latitude, elevation, the code of the stations, and the name of the stations. And the same for temperature. And also we have here the daily data for precipitation, which begins with a lot of missing data, and we have here the end. We have in the middle have the data, and the same for the temperature. Okay, so let's reproduce the examples. Now only three parameters are needed for homogenizing, the three which are mandatory to the function homogen, the short name for the variable, first year and last year. This for temperature. And it finished with a list of all the files that are output, and some suggestions for post-processing, how to obtain averages or trends and p-values, homogenized grids, etc. The same for homogen precipitation. and now this stops with an error because it detects that these series are daily, and the direct homogenization is not recommended. So it suggests to use dd2m function to produce the monthly values from this daily series and homogenize the monthly series first, and then set force equal true. Well, if you set force equal true, you could override this error and go on with the daily homogenization, but it's not really a good idea unless you know what you are doing, because the inhomogeneity thresholds and the threshold for deleting outliers should be very much raised with respect to the default values. Otherwise, you will have lots of splits in the series and lots of deleted values, and it would be lengthening the process very, very much, and in the end you would have absurd result. So let's go to see the results of the first homogenization, that of the temperature. Let's update the contents of the directory, and we can go first to see the output graphics. You have here the first quality control graphics, and you have box plots of every station. You have here box plots of data increments between consecutive values, and you have here the number of lengths of running segments with the same value in consecutive zones of the series. In this case, you see that in all series the maximum number of repetitions of the value is 2. We see here the data availability. You see that there are short series. This one seems to be complete, and this spans through almost all the period, but has lots of missing data. It's a very fragmented series. Most other homogenization packages would be unable to work with this series with so many amount of missing data, but this is not the case with Climatol, which allows you to take advantage of all the climate information of your network. This is the number of temperature data in all stations. The desired minimum would be to have 5 at each time step. The minimum really to be able to identify a value which is an outlier with respect to others would be 3, because if you have one strange, one anomaly which is not reflected in the other 2, you can identify which is the problem. But if you have only 2 series and you have a discrepancy between them, you wouldn't be able to say which is the one which is bad, which is an error, and which is the correct one. But in the end, the only requirement really basic is that you don't have any time step with all data missing in all series. Otherwise, the program would stop, because finally he will be delivering you reconstruction of all homogeneous series and with all missing data filled in. But for that, it needs at least one value to be used as a reference. So we have here a histogram of all the data, a correlogram, which has the correlations are quite good, because these are monthly temperatures, and in summer, in this climate, it's warm season in all stations at the same time, and in winter it's cold in all of them. That's the reason why the correlations are so high. It makes will make a dendrogram with cluster analysis of the stations. But you see that really the similarity between them is not very high, so it's no concern about this. Otherwise, maybe in some cases you could have, for example, a mountain ridge in the middle of your geographic domain, and you could have clusters of series different in both sides of the mountain range. That would show you that there are two climate regimes different, and that would the most advisable thing would be to homogenize both groups by separately. But this is not the case here. So let's go on. It begins with stage 1, which is detecting changes in the mean on step windows. In this case, with the standard threshold for the inhomogeneity test, for standard normal homogeneity test of 25. And here it splits the series here because it found the test of value 53 in series 1. Here also one with 51, series 5. Here it detects with 26 change here, which is really due to this short anomalous period, and in the following iteration it really cuts this inhomogeneous fragment. It makes a histogram of maximum SNHT. This, when you have such a small number of series, is not very much use. If you have, for example, 100 series, you might see that your homogeneous series would be grouped by the left, and you could see the more inhomogeneous to the right, and you find a minimum between them that could help in choosing more tuned inhomogeneity threshold for another running of the homogeneous function. This is not the case here. So it goes to stage 2, where it applies the inhomogeneity test to the whole series. It finds changing in the average here in station 3. No other split is produced. You have here a histogram of number splits and per stations. We have one station found homogeneous, and 4 stations had one split. Number of splits per year, 2 splits coincide in 1989 and 3 in 1994. And finally, it reconstructs all the series. It shows first the anomalies, the spatial anomalies of all the fragments that he has produced. That could serve, for example, if you said, oh, I would like to consider this as a real inhomogeneity, so I would need to lower the inhomogeneity threshold to maybe a value lower than 15. So here also maybe, but the threshold of 25 is really conservative. Climatol tries not to produce false positive detections at the risk of letting pass some small changes in the mean. But I consider that this is better than produce false splits in the series. So after this, you have the final graphics which show you the adjusted series and the applied corrections. You see here the correction 0 shows you the period where are original data, which are in black here in the upper part of the graphic, and this is the correction made to this. You see that the original data began with very low values. This has been corrected here. Also, an outlier has been deleted and this is the correction applied. So the red line is the reconstruction of the series from the last homogeneous period backwards, and also from this small period with lower values it has reconstructed the whole series. Normally other homogenization packages would do only the first reconstruction, which is to go backwards from the last homogeneous period. But Climatol offers you all the reconstructions. This is for station 2, which had that strange, small, short, anomalous period, and really the first part of the first homogeneous period and the last are quite coincident. These are the small correction which have been applied. Station 3 had a split here in 1994, and the correction applied. These corrections have seasonal periodicity. So here, maybe in winter, well, I don't know for sure, but in winter normally corrections needed are less because of the lower solar radiation in temperate climate zones, and in summer they are higher. In this case, the difference is only 1/10 of degree centigrade. And this is station 4, which was very fragmented. You see here which periods had data originally, but no inhomogeneity has been detected, and all series has been reconstructed. And this is station 5 with small change in the mean, with only a few tenths of degree. And this is the final histogram of standardized anomalies. In red you see which outliers have been deleted. If you go to the deleted list, to the list of outliers, which is here, you see that this new version produces two kinds of values, outliers. The ones that he considered as errors, they have been deleted, are marked here with a 1, and the others with a 0 are only listed as suspect errors to allow the user to check for their validity. These are the station code, the date, which as they are monthly values, they are all referred only to the month. Has day 1, but it's really the month which matters. This is the value, the monthly value observed, and the suggested at the time of the detection. That doesn't mean that in the end that would be the value, but it would be similar. And this is the anomaly in standard deviations. So if you really see that this is really a good value, it's not an error, what you would do would be, let's close this. You will look at this, and you could say, okay, I think these are correct values, and this is also a correct value, and I will use a threshold for outliers greater than this. For example, you could put 99, and then all the data would be accepted without any deletion. Let's go on. The residual SNHT by step windows and by the whole series. And this is the final graphic, which is titled Stations Quality Singularity, because you have here the SNHT values and here the root mean square errors. If you saw some station with a very high root mean square error, that could mean that the station has a bad quality, or alternatively it could just point at the fact that that station could be located in a point with a spatial microclimate that will make the values less comparable to the neighbors. That's why we cannot say really that this is about quality. It could be also about singularity. So let's close this output. You have here also the list of breaks. With the month where this break was detected and the value of SNHT. Okay, so let's go to the precipitations, the daily precipitations. They said you should apply the DD2M function first to produce the monthly values, but before that we should check the quality of the daily series. For that we would repeat this command with a new parameter, only QC equal true. So we repeat this and we go here, only QC. The capitalization of the letters is important in R. Equal true. U has not assigned any value to the capital T. You can use it as true. The same happens with false and F, capital F. So it says that one big outlier has been deleted, which is the one we introduced here in the third series. Also, it deleted one value that was lower than 0. And let's see this, the graphics of this quality control check. You see here the outlier of clear error that has been automatically deleted. It's important to make this quality control before producing the monthly errors, because the monthly data, because in the monthly totals these values could be masked. This is the data increments as they are daily precipitations. It may happen that from time to time values around 100 millimeters can happen one day. Maybe the previous day or the following day had no precipitation. That's why you can find these high increments. You see here the run lengths, the lengths of consecutive values which are identical, and you see here which the 10 values we introduced a constant value. We must say that in precipitation, as it detects that it's a biased the data have a very biased distribution, statistical distribution, and are limited by 0, automatically from this test of running lengths, it's excluding the 0 values, because of course in daily precipitation you can have series of many 0 value lengths, and that would produce a very high values here, which would be nonsense. The useful are excluding the zeros. You can change this and exclude other values. This is the data availability. These are the missing data that we introduced, and this is the number of available stations. A histogram of data in logarithmic scale, and the correlogram. And also, always it makes a cluster analysis, and the location of the precipitation series. Okay, this is the last graphic in this quality control check. So let's go to. It's all explained here in the guide. Also, these are some commands which may be a bit complicated to locate this series and to delete them from the data, from the series. Here we read the data, we exclude the zeros from the precipitation, we make a series of identical data. Here we locate where are located the likely erroneous sequence. We delete the erroneous sequence and we write the data again. Let's reproduce this. And now we have the correct version of the series. So now we can apply this function did_it_when to produce the monthly values. We use this parameter val m equal to 1 to obtain monthly totals of precipitation. Otherwise, it would produce averages, which in precipitation has not much sense. And now we can homogenize, well, the homogenized monthly series, sorry, homogenized not, it's just the monthly series, are stored as prec, the short name for the variable, with a suffix of m to avoid overwriting the original daily series. Now we would apply this homogen function to the monthly series, and we in precipitation and wind speed, the standardization of the values, which in tests that I made in the past, is more recommended to make this normalization by dividing by the mean values of every series. This is specified with the parameter std equal to. And we also want in the final graphics to have moving annual totals, not moving annual means. These are the two parameters which are applied here. This standardization std equal to was not applied before, because with daily series it's detected by homogen, by this function. But in monthly values is more, because normally you would not have a big number of monthly zeros. So it is better to force this parameter, to set it. So we apply this, and we have the results. Let's look at them. So now we can go to adjusting the daily series. For that we would use also the annual equal total and also metad equal true. That would be to adjust the series for the breakpoints detected at the monthly scale. Last series readjustment. Okay, so now we can look at this again. You see the precipitation data, the data increments, the run lengths. There are 4 values in the first series, which identical value maybe it's 0.1 or 0.2, but we don't have anymore the 10 consecutive values with an identical data. So this is the data availability at the daily scale. This is the data. This one is the data with 9999, which we introduced and has been deleted. A histogram, correlations, and now it doesn't try to make any detection of breakpoints, because it refers to the breakpoints detected at the monthly scale. I had not shown you that in this case this breakpoint list is empty. It has only the header of the file, because these precipitation series were homogeneous. But if you found breakpoints here at the monthly scale, then what you could do is to edit. If you have the metadata, you could edit these values. Let me close this and illustrate this with the temperatures, which were monthly values, where the breaks are here. So imagine that these were the monthly series from daily temperatures, and you would have here the detected breaks at the monthly scale. You could go to your metadata and perhaps you could find that station 2 had a relocation in this year, but it was not in June, but maybe the 27th of April. Then you would go here and change this date and adjust to this metadata value. They must be dates that are close to the one detected, because otherwise maybe that was a relocation that had no effect on the series, and this was a real detection, statistically detected change in the mean, and couldn't be not reflected in your metadata. So you must know the history of the station, and after modifying this data, these dates with the metadata, you will save the file again. Be careful to save it as comma separated values, because if you use a spreadsheet and you save this, it could change some parameters here, or the format, or whatever. In this case, we did not change anything, and then it goes directly to adjusting the daily series. You see here with a higher variability, which is common with daily values of the spatial anomalies. You could look if you find something strange here, maybe the last fragment, but it's according to the general variability. And you have here the reconstruction. There was a value which was deleted, another one here, and this is the other reconstruction. So these are the standardized anomalies. These are the values which have been deleted, and you have here some also. Let's go to the file with the deletions, the outliers. And you have here a few, the one which indicates that the data had been deleted. There are 3 values, 1, 2, and 3. It may happen, let's see if it's the case here, 98, 88, 93, 93, 10, 6. Yes, for example, in this case, look at this, and look also at this other. Okay, let me. The station number 82 had a very high value, and when compared with the other two stations, it found that it has a very high standard deviation of 19 standard deviations anomaly, and it thinks it's an error and it deletes this data. But this other station, it detects a very lower value, and it thinks that it should be more nearly 141 instead of 89.9. This is a problem which may happen when you have only a few values and they are very close, and you have a very high value here. Then it affects also the neighboring station, because this is very high respected to the others, and this is very low respected to this. So you find that it has the same date here and opposite corrections. So you should check the validity of these values. If this is really an error, you would delete it by hand and repeat the process. Correct, then merda. If this is correct, then you would repeat the process, applying a higher threshold for accepting all values. Then this is the final graphics, and this is the final station quality singularity. So let's go. This has been the showing the examples for this homogeneous function. Again, this is explained in the guide. And which other in the homogeneous functions has lots of parameters that you can see in the standard documentation of the package and of this function in particular. But there are a few that are really important to be noted here. The parameter dz.max is the one that sets the threshold for rejecting the anomalous data. So you can set two values to this with this form, the concatenation function of R for setting vectors of numbers or of other objects, and in this case the lower value would be that would remove data which are higher than the highest value, the 9 standard deviations in this case, and the others between 7 and 9 standard deviations would be listed in the outliers file as suspect, but would not be deleted. So you can control this. Also, normally the same thresholds are used for the right tail of the distribution of anomalies and for the left tail for the lower values. But you can set different thresholds for the lower values by means of the dz.min parameter. The inhomogeneity threshold is INHT, and by default is 25. But as I said, you could use another threshold by reviewing the histograms or the other graphics. If you wanted to force a direct homogenization of daily series, as I said before, this value would have to be greatly increased. For example, using in INHT 2000 and false equal true, that you should check the results to see if this value is good or it should be modified. But normally you wouldn't do that. You would apply the more advanced way of detecting inhomogeneities in the monthly series and then adjusting the daily series according to the break points detected in the monthly series. And also the STD, I commented it before, the type of normalization applied to the data for precipitation and wind speed. It's advised to normalize them by dividing by the mean value of every series by using this STD equal to. If not, you needn't set this parameter. By default, it has a value STD equal 3, which is the full standardization, subtracting the mean and dividing by the standard deviation. You have also parameters to set minimum and maximum values for the variable that you are using. Normally, with the STD equal to, a minimum value of 0 is automatically set. But for example, if you wanted to homogenize relative humidity, you could specify Vmin equal 0 and Vmax equal 100. NREF is the maximum number of nearby series to use to estimate those values. By default, it will use up to 10 if they exist. In our examples, the number of series were much lower, but in normal applications, it would use up to 10 values at each time step if they are available, and 4 in the last step of filling in or missing data. But for example, in homogenization of daily rainfall, the 4 references used by default would smooth the estimated data, because you could have, for example, in the 4 nearby data, in 2 of them there could be 0 precipitation, and in other you could have 10 millimeters, for example. So the average would be 5, and the following day could be the reverse, and you would have another average of 5 millimeters. That would increase the number of days with rain and would decrease the maximum values. So to avoid this, you could set to use only nref equal to only one station of reference. The problem would be that if in the nearest series there is a very high value, it could produce a too high value in the estimated series. But that's the reason why, if you have real strange high values or anomalous values in one station, it's good to let Homogen to reject these values, even if you afterwards check that there was a local thunderstorm or something that could justify this anomalous value. But if it was a local phenomenon, it shouldn't be reflected in the nearby series. So it's better to let it be deleted, and in the end, when you have all your homogenized series, you can reinstate the right anomalous value but real into the homogenized series. This is better than accepting it and letting it alter too much the values in nearby series. Also, you have the WD, which is weighting distance. It specifies at which distance the weight of a neighboring value is halved. By default, they are 0, 0 in the 2 first steps because you are not sure. Maybe the nearest series would be very anomalous, very inhomogeneous, and you don't want to give much more weight to these inhomogeneous values in comparison with the others. So only an average is made with the reference values in the 2 first stages, and in the end it applies a 100 value. 100 value means that at 100 kilometers the weight is half of that would be a neighboring value just located in the same place as the problem series. But you can change it. You can see here how the weights vary with distance depending on the distance, on the parameters that you set to this weighting distance. So finally, the files of results are listed here, and it says that the homogenization results are delivered in this file, which is a binary file. In the documentation of the Homogen function, you can see a description of all the objects it contains, but normally you wouldn't need to load it and to manipulate by hand this data. You could use post-processing functions like the stat. With this you would have averages. The stat, for example, stat equal TND would produce ordinary merda. Ordinary merda is very good, yes. Ordinary low merda. With this stat equal TND, you would have trends calculated with ordinary least squares adjustment to the time with the p-values, and you could have homogeneized grids here. Also important to put stat equal series to have your homogeneized series in CSV format. And I think this is explained here. Stat equal series would produce your monthly temperatures, monthly precipitations, if you apply it to the monthly series, or daily precipitations when applied to the daily series. And you could also have series of homogenized grids in net CDF format. The procedure is explained here. And I think that with this I can finish. Only there are some frequently asked questions about the homogeneous function, how to save results of different tests. You could try different parameters, and to avoid overwriting the results, you can use between every run of the homogeneous function the out-rename function, and you would use, for example, old or whatever that would be attached as a suffix to the name of the variable in all the output results. Then you can run homogen again with obtaining different files. You could change the cutoff level in the clustering analysis if you want to use it to refine the clusters, the groups of stations that you can obtain. You could use reanalysis series as references when you are homogenizing very fragmented series, and maybe at some time step you don't have any data in any series, so you could apply some reanalysis to avoid this condition, to use as a reference in these critical gaps. Or maybe you were homogenizing an isolated series in some remote island in the Pacific, for example, so you would need a reference series, and you could use a reanalysis one for that. For that, you would obtain this series. You have a video about this, an example of how to obtain one from a portal, and you would download this series at the same time resolution of your problem series, and you would just join the data at the end, append the data at the end of the data file, and you would need to add a line in the station file using, for example, the coordinates of the grid point of the reanalysis you have used, put in some, for example, 99 for elevation or whatever value. It's not important, but the code you use, it should begin with an asterisk. For example, this asterisk are 45, 43 or whatever. The name doesn't matter, but importantly use an asterisk before, so that the quality and homogeneity checks will be skipped with those more reliable series. Normally says what homogenized series should I use? Normally you would use for climate monitoring those adjusted from the last homogeneous subperiod, which is the normal behavior of other homogenization packages. But if you are going to use this, for example, to make a plot of averages of climatic map, you could consider using all the means in all the reconstructed series, because some of them could be more affected by local climates, local microclimates than others, and then you would use the more representative according to the scale of the map you are producing. And if the process is taking too long, this is probably due that you are really, as I said before, homogenizing a lot of series at very lengthy, for example, at daily scale, and you are applying a direct homogenization without raising the values of the inhomogeneity threshold and the threshold for rejecting outliers, and then it would be splitting in many iterations the series and rejecting too much data, and then the process is useless. It will take very much time and it's completely useless, so you would cut this process and apply the recommended procedure. And that's all from my side. This video is far more lengthy than I thought, but I hope it's useful. So thank you for watching, and bye bye.